Oh wait, this is how it's gonna work. Right.
You got the chat?
Yeah. All right, so let's start by welcoming you to this VIP safari tour through the Composite Zoo. My name is Werner de Groot and I will be your guide. I'm the happy guy in the front and you guys will be the scared looking girl right behind me. So we're gonna talk about the composite pattern, but first I have to explain what the composite pattern is, of course. And I'll actually give you two separate definitions that appear in literature. Then we know what the composite pattern is. Then it's time to start the tour. And I think the tour will take about half the presentation. We'll see very many different kinds of composites. And armed with that repertoire of composites, we'll tackle low-level queries and a section about how to improve your high-level architecture using the composite pattern. So here we go. 1994, these four guys, which we now call the Gang of Four, they published this really influential book called Design Patterns. And in this book, they describe reusable solutions to commonly occurring problems in software. And these solutions, they call them design patterns. And many of those design patterns are actually quite famous, and you'll see them everywhere, I think. The factory pattern, the decorator pattern, the builder, etc. But there are other patterns in there that are not so famous and not so widely applied. And one of them is the composite pattern. And to me, that's a shame because I think there are many more opportunities to apply this pattern than any of the patterns that I previously mentioned. So I'll take you through the zoo of composites and hopefully you'll think that it's bigger than you thought. So what does the Gang of Four have to say about the composite pattern? Well, they say that you can compose objects into tree structures to represent part-whole hierarchies. Okay, that's pretty opaque. I think Wikipedia has a bit better definition for this, or for me at least. And they say that the composite pattern describes a group of objects that are treated the same way as a single object, a single instance of the same type of object. And a great example of this, which I really like, is that of a load balancer. A load balancer accepts incoming requests and it offloads them to the web servers behind it that do the actual work. But those web servers are hidden from the client, so the client doesn't know they exist. And this is a really powerful concept, I think, because it allows you to scale up and add servers or scale down and remove servers without the client noticing. And those load balancers can become pretty complex, implement all sorts of magic just to maintain the illusion that you're talking to one server instead of many. So sticky sessions and you name it. So here we have a group of servers that is treated the same way as a single server. So all these servers together, they're posing as a single server. They're hiding behind this load balancer. And it's actually the same type of server because every request that is supported by the web servers is supported by the load balancer too, because it will just forward them. So if you look at the interface of the load balancer, it's the same as the web servers. But this is not the example that the Gang of Four give. The Gang of Four talk about grouping shapes. So if you have an application like PowerPoint, like Photoshop, typically those applications allow you to draw shapes on some sort of canvas. And these applications allow you to group those shapes as well. And everything you can do with a single shape, often you can do with a group. So you can move the group around, you can change the background color. And actually you need this. This is a really powerful construct. Because if you're building complex images, you do not want to move each separate object if you want to move the whole image that has many different shapes in it, right? So it's important to have. And we can create an implementation of grouping shapes by first defining a shape interface. And the shape interface has two methods. It has a draw method that accepts a canvas. And the idea is that a shape will draw itself onto the canvas. And it also has a set background color method, and it does the obvious thing. And here we have two implementations of the shape interface, a square and a circle, and how they're implemented, it's not really important. But what is interesting to see is how the group is implemented. And the first thing you notice is that a group implements the shape interface. So a group will act like a single shape, but instead it's multiple shapes. In this example, it's two, it has two properties of type shape. And every time you call the draw method on the group, you will be actually drawing multiple shapes onto the canvas. First, we'll call the draw method on bottom, which will draw itself onto the canvas, and then we'll call draw on top, so that will render itself on top of this bottom shape. So the order in which we pass those shapes to group is important. And the same happens for set background color, right? When I call set background color, it will actually change the background color of two separate shapes. So this is very similar to the load balancer, because in the load balancer you had a bunch of servers that were posing as a single server without the client noticing. And here a bunch of shapes are posing as a single shape by being contained in a group, which supports the same methods as a shape. All right, next definition. I think in 2003, so that's almost 10 years later, but that's still almost 20 years ago, so a long time already. Eric Evans published his book called Domain-Driven Design. I think almost as influential as the design pattern book. And in this book he says, where it fits, define an operation whose return type is the same as the type of its arguments. So it's somewhat similar to the Wikipedia definition of the composite pattern. And here's the example that Evans gives. He talks about a color, and here the color is like an RGB color. It has a red and a green and a blue property. All of them are integers, all of them are numbers. And this color class has a static method called mix, and it accepts two colors and returns a new color, which is a mix of those two colors that you pass into it. And it calculates the mix by taking the average of the red values, the average of the green values, and the average of the blue values. So it's also a little bit similar to both the load balancer and the grouping of shapes, right? So in the shape example, we take two shapes and we combine it into a group, but a group is a shape as well. So we combine two shapes into a shape. The same goes for color. I can mix two colors, combine two colors into a new color. So the recipe for both is about the same. So let me implement and introduce this composer interface. It's a generic interface that accepts the compose method accepts two arguments of that generic type T, and it returns a new instance of that type T. And you can see that we can easily implement a shape composer. It's a composer that accepts two shapes and returns a new shape. And it's actually a group, but the client doesn't have to know, right? It's hidden from the client. I can also implement a color composer. It's a composer that accepts two colors, and it returns a new color, which is the mix of both the colors that we pass. So if we pass it red and blue, I'll get purple back, right? You know the drill. So both implement this same basic general formula. But the composers look a bit different, right? In the Gang of Fours pattern, it's a really simple composer, and I compose two objects by creating a new type of subclass of the interface that I'm composing. In Eric Evans' example here, I just do the whole thing in line. And I think for very simple cases, such as mixing colors, I think it makes sense to do it like this, because there's no need to introduce a whole new type of subclass if you can just really create a new object of the same type. But if it's more complicated, you have more behavior that you want to combine, I think it makes sense to use the Gang of Fours decorator, because that gives you a nice and separate place to put your composition logic, right? Okay, so now we know what the composite pattern is. And now it's time to start the tour. That's why you're here. And we will be seeing many different kinds of specimens, many different beautiful composites. And the very first composite that I'd like to introduce to you is the simplest composite that I could come up with. And it's adding numbers. Adding two numbers follows the same general formula as combining two shapes. Two shapes we get a new shape. Two colors, you get a new shape. Adding two numbers, you get a new number. And indeed, it follows Evan's definition of this composite-like pattern almost to the letter, right? We have an operation whose return type is the same as the type of its arguments. Two ints make a new int. So we can implement a composer for integers. It's our sum composer. It takes two integers and just adds them together. Nothing more to it. Strings are composite too. I can combine two strings to get a new string by concatenation. So just like before, very easy. Here we have a composer for strings that accepts two strings, a left and a right string, and it just concatenates them. What could be easier? From the standard library, Java's list is a composite too. I can combine two lists into a new list by concatenation again. It's very similar to string. And of course it has to be, because strings, if you look inside it, is nothing more than a list of characters, right? So it has to be sort of consistent, and it is. So here we have our first multi-line composer. It's a composer for lists of any generic type, as long as the lists are of the same type. That is important. It accepts a left list and a right list, and then it creates a new empty list, adds all the elements in the left list, all the elements to the right, and then returns the result. So still nothing really fancy. Well, the crazy thing is that booleans, another primitive like numbers, they're composites too. And actually we have two separate options. We can create a new boolean from two booleans by using either the AND operator or the OR operator. And actually both turn out to be quite valid composition operators. Both are valid. So here you see an AND composer and an OR composer. Both are composers for Boolean, but both combine in different ways. So that's a possibility, right? That a single type is composable in multiple ways. And if you go back to that very simple example of adding numbers, you'll realize that there are a lot of ways in which you can combine two numbers into a new number. You can do so with addition, subtraction, multiplication, division, you name it. And two of these feel very much like natural composition operations to me. Like addition and multiplication feels like composition. But when I think about subtraction and division, that's not usually something I associate with composition. And why is that? Well, my first instinct was that it had to do with the fact that I could swap the arguments around for addition and multiplication. 4 plus 2 equals 2 plus 4. And I can't do this with subtraction, and I cannot do this with division. But when you think about it a little longer, you cannot do this with concatenating strings as well. The order in which I apply the strings, it matters. So this isn't it. And you only see why subtraction and division don't feel very natural when you try to combine more than two elements. So if I combine 3 integers by addition, you will notice that it doesn't matter if I first take the sum of 2 and 3, or I first take the sum of 4 and 2, the result will be the same. And this is not true for subtraction. It's not true for division, but it is true for addition, multiplication, grouping shapes, taking the AND of two booleans. And in fact, when it doesn't matter where I put the parentheses, I might as well leave them out. I mean, no use in putting them anywhere if they don't matter, right? And this is a very important property of composites, that the order in which I apply the composition operator doesn't matter. And we will see why when we actually start doing composition operators over multiple elements. Okay, are there any other ways I can combine two integers into one integer? If you just scroll through the math file in Java standard library, you will see plenty. And one example is taking the maximum of two integers. It accepts two integers and returns a new integer, the biggest one. And this is a bit of a gray area, right? Because how true to the word composition are we when I just select one of the arguments and I throw the other one out? That doesn't feel very natural, doesn't feel like a composition operator. But yet it follows the naturalness condition. it doesn't matter if I first take the max of 2 or 3 or the max of 4 and 2, the result will always be 4. So it looks to be, according to the definition, it looks to be a valid composite. And actually it will be a very useful composite. We'll see that later in the low-level queries. So we can write a max composer, another composer for integers that to take the maximum of its 2 arguments. Okay, now we're ready for some more interesting composites, right? Because so far they've been pretty trivial. And event listeners are composites too. So I've written a very minimal definition of an event listener. It's a listener for events of type E, so it can be any type. And the only thing you have to do when you implement this is accept events of that certain type on the onEvent method. And I can compose 2 event listeners for the same event type into one event listener. And here I'm using the composite pattern as defined by the gang of 4. So I'm introducing a new subclass because it's slightly more complicated and maybe it's better to have a separate place for this combination logic. But it's really simple, right? So the composite listener, which is also just a listener for the same type of events, every time it gets an event, it will just pass it on to both first and second. But this is also like, you could simplify your APIs with this as well. Because if you realize that you only have to support one listener for every event type. And if you have a client who really desperately wants to subscribe multiple listeners to the same event, he can always do them themselves, right? By just subscribing a composite listener that multicasts the event to all the listeners that would be interested in this event. So event listeners, they're composites too. Another very common type in Java's ecosystem is the map of keys and values. I can take 2 maps, here with keys string and value integer. I can take 2 maps, one map with 1 and 2, and one map with 3 and 4, and can combine them together into a map that has all of these keys. But you might have spotted a little problem here. What if both maps have a conflicting value for the same key? What do you do? Because you have 2 integers, 2 conflicting integers, and the resulting map only has space for 1 integer. Well, luckily, this is a talk about the composite pattern, and we've learned many different ways in which I can combine 2 integers into a new integers. I can do so by taking the sum, the max, the product. In fact, any composition operation will work here. So this is why a map is only a composite if the value type is a composite. So a map is only a composite if the value type is a composite. And here you see the composer for map. It's really the first interesting piece of code we've seen so far. And you see that it needs a property value composer. It needs a composer for values. So what does this thing do when it gets 2 maps? Well, first it makes a copy of the left map because it always has to return a new thing, right? And then it iterates through all the keys and values of the right map. And it tries to add those values to our result map. And I use the merge method here. And the merge method lets me define like this conflict resolution operation. So every time there's already a value in the map for that, the third argument here lets me decide what the result should be. And I could use my value composer here. And this I could use for my conflict resolution. And then I just return the result, right, when I'm done. And here you see the value of the composer abstraction. So it let me write generic composition operators that depend on other composers to do the work. So this map composer works for if the value is an integer and I want to take the sum. It works for maps of strings where I want concatenation. It works for all kinds of values, as long as they're composites. And this is part of the category of composites that I'd like to call symbiotic composites. So it's a map composer which has a symbiotic relationship with some other type of composer, a value composer. So it needs this other composer to do its work, just like the crocodile here needs this little bird to clean the teeth, because else it would get infected and nobody likes this. So we'll see lots of symbiotic composites in a little bit. But first, one example. Here's a map composition operator that adds the integers, the values. So we get 2 and 20 is 22, etc. You can follow it. And here is what you get when you switch. Instead of one integer, you switch to a list of integers instead. And lists are composites, right? We've seen that before. And the smartness of this map composer and the list composer together make sure that I collect all the values. I get like a multi-map for free. So my tip to you always is, if you have a symbiotic composer and you have trouble deciding how you want the value composer to look like, well, try to see if you can switch to a list, because list is automatically a composite. And unlike taking, for example, the max of an integer, you never lose a value. All the values are always there. So it's a good tip to remember. And we'll see this tip again in a couple of slides. Interesting one. Java 8 lambdas, the functions, they're composites too. And how would that work? Suppose I have two functions from a parameter type P to a result type R. How can I combine two functions into one function? How would that work? Here's how. On the right side, you see the resulting function, and on the left side, you see how it's implemented. So you have this input, this parameter, and you pass it to both the left function and the right function. So you have now two result types, one from the left function and one from the right. And then you need to combine those two R's into one R again, which will be the result type of our composed function. And we need another composite for this. This is another symbiotic composite. And the funny thing, to me at least, is that apparently it doesn't matter what the parameter looks like. It doesn't need to be a composer. And in fact, it doesn't even matter if there's like 1 or 5. We just pass them along to both the functions, and only the result type matters. Only the result should be composable. So here we have a function composer. It's a composer for functions from P to R. And like I said, you need a result composer for this. And to combine two left and right functions, I get a new function that takes a P, passes it on to both left and right to get two R's. And then I use the result composer to combine those two R's into one other R. And this will be the result of my composed function. Excuse me. This, I promise, the tour is almost over because it's getting a bit boring now. Optionals, Java 8's optional values, are composites too, but only if the potential value in the optional is composable too. So for example, if I have two optionals with a value, the result needs to be an optional just with one value, right? So I need to combine them. But if I have one empty optional and the other one is none, doesn't matter if it's left or right, the result will just be that single non-empty optional. And if both optionals are empty, the result will be empty as well. So this is another symbiotic composite. It places the restriction that the value, the potential value in the optional, is a composite. But there's a different way in which I can combine two optionals that does not impose this restriction. And I changed the slide, but it's hard to see. It's in the upper right corner. This is the optional composition operator that just selects the first non-empty value. So if I have two non-empty values, like 1 and 2, it just selects the first one. So it's optional 1. And if one of the two optionals has a value and the other hasn't, well, then I use just the value that's there. And when I have two empty optionals, well, the result will be an empty optional. So two ways, again, in which this optional can be a composite. Okay, so this concludes... I have to implement it first. Crap, I missed this slide. So it's a composer for optional, and it uses the OR method. And OR was only introduced in Java 9. And instead of taking that alternative, you have to give it a supplier of the alternative. But again, it's just one line, right? So now finally, the composite tour is finished, and we've learned about a bunch of composites. And in fact, we've learned about certain types which are composable in multiple ways. And I think the important takeaway is not that you remember exactly how all these things are composites. I think it's important to remember that they are. And if you have need for one of them, most of these implementations are pretty simple, right? You can derive them on the spot if you have to. So don't worry if you don't quite remember how all these things are composites. Just remember that they are. So now we're on the topic of applications, and we'll start with the low-level queries on your in-memory data structures. And to discuss this, I want to discuss first, because we know we can combine two elements into one element, but can we combine multiple elements into one element as well? Because things in programming almost never come in pairs of two, right? You typically have lists of hundreds, maybe thousands of elements. Can we compose all these guys together to form one element? Can we, for instance, sum these 6 numbers to get 21? Well, of course we can. And we can use the reduce method on Java Stream for this. And the reduce method just takes a single function, and it's our composition function, and it can compose all these integers together by taking their sum. This is why this method is called reduce. That's at least why I think it's called reduce, because it reduces 6 integers into one integer. And the result, you might have noticed, is not an integer, but it's an optional of integer. And this is to safeguard that reduce is not called on an empty string, because taking the sum of an empty string is nonsense. So that is why the optional is there. So how does Java do this? Well, it does so by first taking the sum of 1 and 3, then taking the sum of the results 4 and 2, which is 6, 6 and 6 is 12, and so on until we get 21. But this is just one option, because Java might as well work from back to front. You know, first sum the last 2 integers and work its way back to the front. And here we're using the naturalness condition. It doesn't matter in which order we apply the composition operator, the result will always be the same. And in fact, Java might as well calculate the sum of the first 2 integers in one thread, the second 2 integers in another thread, and the last 2 integers in a third thread, and then sum all them up together to get 21 again. It's the same answer. So here you see, and it's really not that hard to do this in Java. You can just use the parallel modifier on stream, and you get like parallel processing, parallel reduction of your stream for free. And you see that you can only do this if the order in which the composition operator is applied doesn't matter. So this would not work for subtraction. Okay, thanks, Siri. Okay, can we, for example, take the maximum of a stream of integers? Well, we can do it simply by switching the composer. First we use the sum composer, here we use the max composer. And it works a bit the same. Same principle, Java will take the maximum of the first 2 elements, which is 3, then compare 3 with 2, which is still 3. And then 3 and 6 will give 6, and 6 is the biggest one in there. So every other combination with 6 will return 6. So here's how you can, by swapping around the composition operator, get different kinds of statistics on your streams. And we can use another trick. We can use the same composition operator, but apply a pre-processing step to, for example, count the number of elements in a stream. And we do this by mapping every element to 1. So we make every element count as 1. So we get a stream of 6 ones. And if we sum that together, we get the count of the stream. I wouldn't advise you to actually calculate the length of the stream this way, but it's good to know that you can. Can we use our AND and OR composers perhaps? Well, first, of course, we need to transform the integers to booleans to get a stream of booleans, but then we can use the AND composer and the OR composer. So let's say we check whether every element is even or odd. So we have a stream of 1, 3, 2, 6, etc. And the stream will then contain false, false, true, 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 false, because only those 3 numbers in the middle are even. And if you use the OR composer, remember that OR returns true if one of the arguments of OR returns true. So in this way, we can check if one of the elements in the stream is true, or one of the elements in the integer stream is even. And AND operation is the exact opposite. It only returns true if both of the arguments are true. So in this way, we can use the AND composer to check if there's just a single false in there will cause a false, right? So we can check whether all elements match a certain predicate, or some of the elements match a certain predicate. So this is the usefulness of Boolean composers. Now, interesting question. Would I be able to calculate the average of a stream? The answer is yes, but not in the way you think, maybe. Because you might be tempted to write this average composer. It's a composer for doubles. It takes two doubles and just averages those two. And what happens if first I have to convert every integer to a double, but what happens if I compose all those doubles together using my average composer? Well, whatever happens, it's not the average. This is just not how averages work. To calculate the average of a stream, I have to divide the total sum by the count of the stream. So you can't do it with this shortcut. It doesn't work. But we can still do it using composition operators. And of course, we can calculate the sum and in one iteration, and then do another iteration to calculate the count, and then divide the two. But I'd like to avoid that if I can. I'd like to do it all in one pass. And to do this, I introduce an average class, which has a separate spot for the sum and a separate spot for the count. It's just a value class, nothing interesting, just a constructor and two getters. But what is cool is that this average is composable. I can write a composer for averages. And if I want to compose two averages, I just add the two sums, and I add the two counts, and wrap the whole thing up into an average, and that will hold the right sum and the right count for both averages. So then what I do? First, I map every element to an average. And this is another way of saying I want to know what the average of one element is. This is a really weird question, but I can answer it. Because I need a sum and a count. And what's the sum of one element? It's the element itself. What's the count of one element? It's 1. So I can calculate the average of each element. And then I can compose all those averages together so that I hold the total sum and the total count. And then I just divide the two as a post-processing step. So it works, but I don't think it looks pretty. I would not be able to sell this to you with a clean face. Okay, another way we could use, like my challenge for myself was to use every composer in this presentation that we talked about in the tour. And I think it worked. Here I'm trying to use the map composer, a map from integer to integer. And what I do, notice that this is a different stream of numbers. You can see that the number 1 is in there 3 times, and the number 3 is in there twice, and 5 is in there just once. And what I do is I take every element and I create a map from integer to integer. And I put into that map the element itself, so the key is the element itself, and the value is 1. So I create like a count map, a map that contains for every value how often it finds it. And for one element, it's a trivial thing, right? But if I compose all those maps together with our beautiful map composer that we've seen earlier, what I get is a map that contains for every number in the stream how often it occurs in the stream. So, you know, this is... I really like playing with these composers, with these different composers, to see what kind of cool statistics I can calculate over my stream. And the stream is what I call my in-memory data structure. But again, like the previous example, I don't think this reads nice. I don't think this communicates clearly to someone reading this what is happening. You can follow along right now because I've basically explained all of this. But if you encounter this for the first time, you might be wondering, like, what's happening? So I think the composer interface is just a bit too close to the metal. It's a bit too, it's not abstract enough. And I notice that there's a common theme occurring. And that's that I need a pre and a post-processing step to combine with every composition operator. And here you see the case with averages. So first, as a pre-processing step, I need to map every element to an average of that single element. And only then can I use my reduction, my composition operator, and then I have to do some post-processing. I have to divide the sum by the count. And this is the same in a lot of other examples. Here, for instance, for counting numbers, I have to map every element to 1, sum all the ones together, and then I don't have to do any post-processing operation here because 5 is already the answer. But in the most general case, I have a pre-processing step, a composition operation, and a post-processing step, right? So I'll introduce another interface. It's called reduction, and it has 3 type parameters. It has an I, which stands for input. It has a C, which stands for composite, and it has an O, which stands for output. And these correspond to the layers in the diagram you've seen earlier, right? And it needs 3 implementations for a pre-processing step, and I call that toComposite. We transform an input element to a composite, and then we need to reduce all those C's together into 1. But we know that if we have the reduce method, we only need to be able to do 2 elements into 1. And then we get the many elements into 1 for free. And then as a post-processing step, we apply the toOutput function. And then I can give you an apply method on this reduction as well. It takes a stream of input elements and returns an optional output element. And it just does the pre-processing, the reduction, and the post-processing. Nothing really scary, I'd say. So here's an implementation. It looks really long, but it's not that hard, I think, of the average reduction. And you can see the 3 type parameters, integer, average, double, which means that the input elements are integers. And then for every integer, I calculate an average, compose that, and divide the sum by the count to get a double. That's where the type parameters come from. And it's just 3 methods with implementations we've already seen. And way at the bottom, I create a new average reduction, and I apply that to the stream. So you can see that I can hide all this pre and post processing stuff into the reduction and get a really clean interface back. So I can write beautiful reductions. I can write average. I can write any, all, product, count, min, max, you name it. For almost any composition operator I can think of, I can write a reduction. And the reason why I call this section low-level queries on your in-memory data structures is because these remind me a lot of SQL aggregates, like sum, max, min, and average. And these SQL aggregates actually use the same underlying principle. They just compose values together. And many of the reductions you see are supported by Java Stream interface natively, right? You can do any on a stream and no need to do tricks with reductions and compositions. But now that you know how to write the easy things using reductions, you can write some complicated things as well. So now we see the crown jewel of this section, like a really interesting low-level query on your in-memory data structure. And it's calculating the standard deviation of a stream of integers. And you should be scared, right? This is pretty hard. I want to focus on this is the definition of the standard deviation, and I want to focus on the rightmost part. And it's the square root of, you see that weird symbol that you probably don't know. It's the sum symbol, and it says I take the sum of the x squared. So it means the sum of all the elements squared. And I divide that then by n, which is the count. And from that I subtract the sum of all elements divided by the count, and that whole thing squared. So this is the definition of the standard deviation. And I can express this beautifully in Java as a reduction. And it reads almost as if I was just telling it to you, right? It's the sum of the square divided by the count, minus the sum divided by the count squared, and then the square root of that. So I don't think you can get it any more concise than this. So I don't have time, unfortunately, to walk you through an implementation, but I can sketch the implementation so that you get a sense of how to implement this. And it starts by realizing that the standard deviation is a reduction, but count and sum are reductions too. And here I divide a reduction by a reduction. How would that work? And sum divided by count is also a reduction, right? So I can combine two reductions into one reduction. Have you heard that before somewhere in this talk, maybe? So how would you combine two reductions? It works a little bit like this. So let's say we have two reductions, a sum and a count, for example. And each takes the same input element. They take integers, but they map it to a different composite. And the composite is different. So I get from every reduction, I get one final composite back. And then I apply my unique post-processing operation to that reduction. So I get an O1, an output 1, which is different from the O2, which is also the output from count. And how can I divide these two? Okay, don't be scared. I'll walk you through it step by step. It's not as bad as it seems. So we know that I can map every input element to both a C1 and a C2, right? A composite from the sum and a composite from the count. And I can combine these two into just one blob, one object that contains both composites. And it's very much like average, which just holds a sum and a count separately, but then just a little bit more abstract. It just holds two composable objects. And because two composable objects in one object is composable too, because we saw that averages are composable, because the components are composable. So it works the same way. So I can reduce this blob into one blob. Then I can split it up again to get one C1 and one C2, map each one to its own unique output element, and then only at the end I can divide the two, right? So that combination operator, the divide by, it only comes in way at the end, when I'm already done calculating both the output elements. So I have a reduction here, sum divided by count. It's a reduction as well, according to the recipe from the previous slide. And you see here minus just subtracts two reductions. I have Siri who wants to talk to me. And the only difference between the minus combination and the divide by combination is that final step where we actually combine the two output elements. Okay, so here's how to combine two reductions into one. But then we have, for example, this squared thing. How does that work? Well, what we need to do is take the sum, divide it by the count, and then at the end, square it. So squaring is another post-processing operation. And you know, you are all very smart guys, so probably you can write a reduction with an added post-processing step. And the same goes for taking the square root. It's just another post-processing step. And then the final component that I haven't explained yet is the sum of the square. And how this works is that you just square each element and then calculate the sum. So this is just another pre-processing operation. So you can see that it's not that hard as you might originally think. It's just adding pre- and post-processing operations and combining reductions. So to close this up, because what have we achieved? We've achieved this very complicated thing, which we can express really concisely in Java. We can run this, and it will only take one iteration over the stream, unlike just calculating the sum and the count separately. And also, you can parallelize this. So you can calculate the standard deviation over truly gigantic data sets. You don't have to do it in one thread. You can do it in multiple threads or even in multiple machines, right? And this is how big data frameworks like Spark or MapReduce, this is how they work. They require that you have these natural composition operators to be able to distribute it. Okay, so this was the section on low-level queries. Now on to the final section, and that's talking about architecture. And the composite pattern was originally designed to help your architecture, right? But I briefly want to discuss what would happen if you didn't know the composite pattern. What would happen if you did not apply the composite pattern at your architecture level? Well, let's take a look at that shape example, grouping shapes together. And what would happen if group did not implement the shape interface? So it was not just a bunch of shapes posing as a single shape. A group would just be a very thin wrapper around a bunch of shapes, an entirely different object. So if I have a bunch of shapes, let's say I want to group two shapes together, I create a group object, and that group object is a totally different object than shape. So if I have an image with a property shapes, that's not enough anymore. I need a property for groups as well. And also I need some mechanism to, when I want to group two shapes, to extract those shapes from the shapes property, group it, and put it back in the groups property. So it's more complicated. And also we've lost something along the way. Because previously we could group groups. Because we know how to group shapes, and a group is a shape. So we're able to create a group that contains groups, that maybe contain shapes. So we can group groups. And this is really powerful, and we don't have that anymore. And if I want to create a group of groups, maybe I need to introduce a new object, like a multi-group, for example. And what if I want to combine that? And on and on and on and on. And it seems ridiculous almost to do it like this, right? It almost seems like a wasted opportunity to apply the composite pattern. And in fact, it's not as ridiculous as it sounds, because we're used to doing this in our architectures all the time, right? We create these huge object graphs, these big hierarchies of objects. We seem to love them. And it's the most straightforward thing to do. And it takes real experience to recognize a chance for the composite pattern in there. And when you do, things just get so much simpler. Because a group is just a shape as well. So you stay within the layer of shapes. So if you have an image, it just needs a shapes property. And in fact, an image, it's just a container of shapes. And we already have such a thing, right? It's a group. So an image could be a shape as well. And what you get for free here is that because all of these things are shapes, for example, an image is a shape. And what we can do is embed one image into another image. So you can just combine them in infinite ways, and you get so much flexibility, and your architecture just is so much cleaner than if you create this hierarchy. So it's really valuable, I think. And what I can do to show you the trick, how can you find the composite pattern in your code base that will solve everything, that creates from complicated object graphs just very simple architectures. How can you do that? Well, I could do it like the first section, right? I just give you a bunch of examples. We've seen an example with the load balancer, which is an example of a high-level component in your architecture. And it is a composite, but it just takes some experience to realize that it is. Another example that I could give is transactions. I can combine two transactions into one transaction. And if one of the transactions fails, the other will be rolled back as well. So that's really awesome. But I don't think that giving you these examples will teach you anything about finding composites in your own code base. So instead, I'm going to share with you a simple recipe to find or create composites in your code base. And this will not give you those brilliantly creative composites like the load balancer or the transaction, but it will provide a starting point to apply the composite pattern and make your architecture just so much simpler. And the recipe is simple, like everything, I think, in this in the composite pattern. And it says that an object is composable if all public methods return either void or a composite themselves. And the void ones we'll discuss first. And we've already seen this in the group example, right? Because the two methods on the shape, they return void. And it's really easy to compose those. We just sort of pass through the call to all the individual components. So really easy. The voids. But what about methods that do return a value? How would that work? Well, we already know that from the example from before with the Java 8 lambdas, that two functions can be composed if the result type is composable. place no restriction on the parameters, but the result type needs to be composable. And that's the same principle that applies here in this simple recipe. The return values from your method needs to be composable. And we could have already seen that this color was a composite by just looking at the return types. They're all integers. And we know so many ways to compose integers. And if I want to mix two colors, I choose the way to compose that seems most natural to that, right? It's taking the average of the red integers and taking the average of the green integers. But then I have to admit something to you. Because composing two colors, it's not a natural composition operation. Just like we've seen that averaging two doubles doesn't really work well for a whole stream. And you can easily see why that is. Let's suppose I want to mix black, black, and white. If I first mix black and black, I get black again. So nothing changes. But if I then mix with black with white, I get medium gray, 50% gray. But if I do it in another order, if I first mix black and white, I get that medium gray. But I have to mix it with that other black still to get dark gray, 25% gray. So not all composites that we've seen are natural composites. And it's debatable how bad that is, right? I think mixing colors is still a very valuable concept. But you have to be aware. You have to be aware if you, for instance, reduce over a stream, in what order that reduction takes place. Because you might get a different result if the order in which the reduction takes place is happening in a different way than you expect. And you know that doing this in parallel is off the table. So be aware. Always check in your recipe whether composites are natural. Okay, now on to something that actually does something. We've seen void methods. We've seen simple getters. What about objects that actually perform a function, like the elephant repository? It supports the typical CRUD operations that you can expect from a repository. You can create an elephant, read it, update it, delete it, the works. And let's suppose we have two implementations. An implementation that stores elephants in a relational database, a database elephant repository, and one that uses an in-memory data structure to keep track of elephants, the in-memory elephant repository. Can we combine two repositories into one? We can. And actually, in a very interesting way, we'll get a cached version of our database elephant repository by just applying our simple recipe. So we will be able to create a very simple architecture in which I have a normal elephant repository that talks to the database, or a cached one without any added load to my architecture. So following the simple recipe, we can see that create, update, and delete, they all return void, so they're easily composable. So if I call create with an elephant, the create call is passed on to both the in-memory elephant repository and the database elephant repository. And this is what we want, right? If we add an elephant, we want it added to the database, but also to the in-memory data structure. And remember that the in-memory elephant repository, and whenever our app reboots, it will be empty. So the database elephant repository will probably contain more elephants than the one in memory. Okay, then that last method that we haven't talked about, it returns an optional of elephant. Is that a composite? Well, optionals are composites, but only if the potential value in the optional is a composite too, right? And that seems like a dead end, because two elephants, how can I combine them into one elephant? But we've learned a second way in which an optional is a composite, and that does not place any restrictions on the potential type, right? It's the optional composite that just selects the first non-empty value. And that's exactly what is very useful here. So first it checks the in-memory elephant repository, and if that has a non-empty optional with an elephant in it, well, we're done. We don't need to talk to the database. But if the in-memory elephant repository is empty, then we have to use the result from the database elephant repository. So here's how this recipe is very simple, but also you have to know a bunch of different composites. You have to know that optional is a composite, and you have to know that it is a composite in multiple ways. So it's a simple recipe, but you do need some experience again. Now, on to the very last subject of this talk, and I think this is where it all will come together. The simple recipe applied to an account validator. Very simple interface again. It just checks, returns true or false if an account is valid or not. And you might be tempted to create like this single canonical implementation of an account validator. And everybody should use that account validator, right? It's where all the business logic is contained. But the decorator pattern gives you an alternative, one that I like and prefer over that canonical account validator. And it tries to lead you in a direction where you write a lot of very small account validators. So an account validator that only checks if the username is valid. An account validator that only checks if the email is valid or the password is valid. Very small and easy to write validators. And if account validator was a composite, I could combine all these account validators into one account validator. And that will be my canonical implementation. So, and it is, because we see that the isValid method returns a Boolean, and Boolean is a composite. And because we know that an account is valid only if all the validators return true, all, we've seen that before, we need to use the AND composer, right? So here I've written an implementation that accepts an account and returns true only if the left validation succeeds and the right validation succeeds. And I could have written this in a different way. I could have used the composers that we wrote. It looks a bit more difficult, but it's fun to see this in action, right? So I want to compose two functions, two isValid functions, and they take an account and they return a Boolean. So those are the type arguments to function composer. And I want to compose those two Booleans by using AND. So that's why I pass in an AND composer. Then I compose the two functions, the isValid function on the left account validator and the isValid function on the right account validator. And then I get a single function, and then I can give that an account to get a Boolean back. So a bit more complicated, but it's fun to see that it works like this, right? And in this way, I can write a stream of account validators, a whole bunch of them, as many as I like. And I can reduce it all to one account validator. So this is why everything comes together here, right? By using the composition operator that I already have, which is the constructor for the composite validator. Because it takes two validators and returns a new one, which is a composite validator. So a couple of things that I really like about this. I can mix and match validation rules. So if I have an account validator, I can easily create two variations of it. For example, one to validate new accounts and one to validate existing accounts, for example. And I do not have to copy paste anything. I do not have to rewrite anything. Another thing that I like is that this adheres to the solid principles. The single responsibility principle. Well, you bet that single username validator only does one single thing, right? And it does it probably really well. Email validator the same. The open-closed principle, which says, well, we can without modifying any code, I can still add validation rules by just creating a new validator and putting it in the stream. So I don't have to change existing code to add functionality. So also those solid principles, those really fundamental underlying principles for clean architecture, basically, they really apply here. And did I have another thing? I don't think so. No, I think this is what an anticlimax. This is, I think, the last example. I want to give you one final tip because it's really hard to come up with a proper composition operator for your return types, right? We've seen that. It takes some experience. And it's not always possible as well. If we have two elephants, we can't compose them into one elephant. But if we would have the freedom, and I'm not saying we have the freedom always, but if we have the freedom to switch from elephant to a list of elephant, well, a list is always a composite. So we get immediately a composite for free. And if I have a list of elephants, I can always choose to reduce later, right? In some other piece of my software where I do know a proper composition operation for elephants. So simple recipe, with a bunch of tips. And this concludes the section on architecture. And this concludes the presentation as well. We've learned a bunch of things. We've learned 2 definitions of the composite pattern. We know that there's a rule which separates natural composites, which are safe to use in multi-threaded environments, from non-safe composites. We've learned that a type can be a composite in many different ways, and we can reduce many different composites into one by using reduce, which we can really use very handily for our queries. And we concluded with a recipe to find or create composites for your architecture. And with this, I'd like to thank you for your attention. And if you have any questions, I have to admit I haven't been looking at the chat, but if you have any questions, feel free. No questions?